Hello students, today we will discuss transistor biasing and load analysis. In transistor biasing and load analysis, we will discuss first we will discuss introduction, we will go for transistor components, transistor biasing, stability factor, thermal runaway. Next we will see fixed bias, emitter bias, next bipolar junction transistor as an amplifier. In this first we will start introduction. In introduction, we will use the term transistor. What is transistor? Transistor means transfer resistor. In the previous version of the transistor is vacuum tubes. After vacuum tubes, these transistors are invented in Bell Laboratories. This transistor is of again two types, unipolar junction transistor and bipolar junction transistors. In unipolar junction transistor, only one type of majority charge carriers are present, whereas in bipolar junction transistor, two types of majority charge carriers we are using. In two types of majority charge carriers, holes and electrons, both are participating in the circuit action. Whereas in unipolar junction transistor, we are using either electrons as a majority charge carriers or holes as a majority charge carriers. In bipolar junction transistor, both electrons and holes both are participating in this. This transistor is a semiconductor device which is used for the amplification purpose. Whatever the switch we are using at home, on off switch, this on off switch means it is a transistor. Transistor can be operated in off mode or on mode, or this transistor switch is used for the electronical signals. These transistors we will found in all electronic equipments in from microprocessor to the satellite communication to the cellular infrastructure, in everywhere this transistor is a basic element. The transistor consists of three terminals: emitter, base, collector. We can interchange these terminals. You can take the combination emitter, base, collector, or base, emitter, collector, or collector, base, emitter. Means here we are concentrating on the middle term. Whatever the middle term we are using, that configuration we are choosing. So, if the middle term is base, we will call it as a common base configuration. If the middle term is collector, we will call it as a common collector configuration. If the middle term is emitter, we will take it as a common emitter configuration. So, this transistor is operated in three ways: common base, common emitter and common collector. Next we will see the transistor, as we said, discussed emitter, base, collector. This emitter, base, collector transistor can be categorized as either PNP transistor or NPN transistor. What is PNP transistor? P type, N type, P type. In this PNP transistor, we have two diodes. PN is one combination, NP is another combination. So, N type material is sandwiched between the two P types of materials is called as PNP transistor. In this PNP transistor, whether we can use emitter base junction or collector base junction. This emitter base junction, collector base junction is based on the middle terminal what we are using. The next transistor we are using is NPN transistor. In what is NPN transistor? We have N type material, P type material, next we are using N type material. Here P type material is sandwiched between the two N terminals is called as NPN transistor. Again here also we are taking emitter, base, collector combination. Whatever the collector side we are using, that is called as collector region, the middle part is base region, and the input base region and the input part is emitter region. So, here the conclusion is transistor is of two types, either PNP transistor or NPN transistor. And one more important point is transistor consists of three terminals: emitter, base, collector. Using this, now we will see further how the transistor looks. So, PNP transistor, NPN transistor. How to differentiate PNP transistor or NPN transistor? By current flow direction. For PNP transistor, the current direction is always inside. So, how to remember? Wherever N terminal is there, the the current arrow is inside. Whereas for NPN transistor, in NPN transistor, the middle term is P. The two cornered edges what we have? in the corner edges we have N. So the arrow is outside for the NPN transistor. In the PNP transistor, here we are taking the middle region as a base, and the two edges we are concentrating, one as a collector and another one is emitter for PNP and NPN transistor. In transistor current components, here IE is there. What is this? IE represents emitter current. This is connected across the emitter, so we are calling this as emitter current. And another current we have, that is base current. This base current is represented with IB. Next another current is collector current IC. So IB, IC, IE, three are completed. Next we have two junctions in this diagram. What is the junction? The junction J is called as junction across the emitter. Again the junction JC means junction across the collector. Here three parts this diagram we have. What is the first part? The first part represents P, next part represents N, the third part represents P. Next here we have two power supplies. Positive terminal is connected to P, negative terminal is connected to N. So this positive connected to P, negative is connected to N. This forms as a forward bias region. Next another partition we have N and P. In this N and P, P is connected to negative terminal of the battery, N is connected to the positive terminal of the battery. So this region acts as a reverse bias. So in this diagram we have two regions. PN combination is forward biased, NP combination is reverse biased. Next few more terms we will discuss here. What is IHE? What is I of IE? Next we will see what is I of CO. Next we will see what is I of HCO, I of ECO. Next what is I of HC. Now we will see what is I of HE. H means holes, E means emitter, I means current. So total I of HE represents current across the emitter. Whatever the current we are using, that is whole current. I of HE represents whole current. Next come to I of small e capital E. What is this small e? This small e represents electrons, capital E represents emitter. So what is this small I of E? Capital I of small e represents, this is the electron current. This I of HE acts as a majority charge carriers. Why this I of HE acts as a majority charge carriers? Because we are using P. P means holes. If P is holes, this I of HE acts as a majority charge carriers. This capital I of small e capital E acts as a minority charge carrier. So the first partition is completed. Next we will come to the second partition. In the second partition what we have? I of HC, I of small e capital C. What is this I of HC? Whole current across the collector. If we are using E means emitter, capital E represents emitter, capital C represents collector. So what is this I of HC represents? Whole current across the collector. Next this whole current across the collector acts as a majority charge carriers or minority charge carriers. In the collector, holes acts as minority charge carriers. Here P region, so holes acts as majority charge carriers, electrons acts as minority charge carriers. Suppose imagine that there is no emitter connection. If no emitter connection means I am treating E emitter as open terminal. Suppose emitter is open, whatever the current is flowing across the collector, that is called the reverse saturation current. Here I of CO represents reverse saturation current. Again this reverse saturation current I of CO is the combination of reverse saturation of whole current plus reverse saturation of electronic current. All these points, the description of all these currents, now we will see one by one in steps format. What is first IE? IE represents emitter current. This emitter current consists of again two currents, whole current as well as electron current. This whole current is represented I of E equal to I of HE plus I of small e capital E, where I of HE is due to the forward bias in holes. H represents holes which in the P region, whereas small capital I small e capital E, what it represents? E represents electrons, capital E represents emitter. This small e capital E acts as a minority charge carriers. So total I of HE is majority charge carriers, I of small e capital E is the minority charge carriers. We will come to the next point. In the next point, the ratio of What is the ratio? The ratio of I of He by I of small e is equal to the conductivity of p type material to the n type material. What it means? I, capital I of He by capital I of small e is equal to conductivity of p type material to the conductivity of n type material. As we discussed only about majority charge carriers in both the regions, we also have minority charge carriers. These minority charge carriers is represented with I of Pn. This I of Pn is across emitter. Another we have I of Np. This I of Np represents across the collector. So, in emitter region, I of Pn is the majority charge carriers, minority charge carriers. I of Np is the minority charge carriers across the collector. After this, out of emitter base collector, emitter is heavily doped compared to the base. Emitter is heavily doped. Whatever the current across the emitter is, we are taking EIE. So, a small only 5% of recombination is taking place across the emitter and base. So, the remaining holes is forwarding towards the collector. That is mentioned in the third point. The transistor emitter is heavily doped as compared to the base. So, whatever the electron current across the emitter, we are neglecting that one. Next, we are using PNP transistor. So, what is here input current? We are taking input current as IE. So, across the output, whatever the current we are taking, that one as a collector current. Next, in the fifth point, all the holes crossing from emitter to base junction, whatever across the input, the same holes is not going to the collector region. Why it is not going to the collector region means some of the recombination is taking place across the base region. So, whatever the input, the same is not coming to the collector region. Next, we will see what is I of. So, this current is over, emitter current is completed. What is emitter current we used? I of He plus I of Pe. Now, we will see here base current. The base current is I of He minus I of Hc. Here what is I of He, what is I of C? I of He is the holes current across the emitter minus holes current across the collector. This I of Hc we can observe from the figure. Where is I of Hc in the figure? On the collector region. We have collector region I of Hc. So, from this current, from this diagram, we will use I of B equal to I of He minus I of Hc, which is represented in the diagram. Next, we will come to the next point. As collector junction is reverse biased, this reverse biased PN junction diode producing reverse saturation current. That reverse saturation current is representing as I of CO. Again, this reverse saturation current is also combination of two currents. This reverse saturation current is showing in two combination. What are the two reverse saturation currents? I of HCO plus I of ECO. So, what is finally I of CO? I of CO represents I of hole current as well as electron current. So, here we are using another current called collector current. So, what is collector current? Collector current is I of Hc plus I of CO. So, in this topic we are mainly discussing on four currents. Suppose if the question is asked like what is transistor components? In transistor components, from the diagram only we can say the three currents. What is the first current we have? I of E. What is the formula of I of E? I of E means emitter current equal to I of He plus I of small e capital E. This is one formula. Next, we have another current. What is the another formula? Base current. What is base current formula here? The base current formula is I of He minus I of Hc. Next, we have another formula, collector current. What is collector current? I of Hc plus I of CO. Here I of CO represents reverse saturation current. This reverse saturation current is again having holes combination as well as electronic combination. Next, we will see in active region we will get collector current. What is this collector current represents? Collector current IC equal to alpha times of IE plus reverse saturation current. What is this reverse saturation current? Reverse saturation current is I of CO. So finally I of C equal to alpha IE plus I of CO. So the input current is a combination of base current plus collector current. Again in this current components we have another term called alpha. This alpha is the ratio of collector current minus reverse saturation current. What is collector current? Collector current is IC minus reverse saturation current is ICO by, in the denominator I am taking the emitter current IE. So overview of transistor components is write about emitter current, base current, collector current, also the current gain alpha. Next we will see about transistor biasing. What is transistor biasing? In transistor biasing means I want to keep emitter base junction in forward bias condition. My main intention is keep your input side forward bias condition and keep your output in reverse bias condition. To keep input in forward bias condition, we need proper voltage and current is needed across the collector to VCC terminal. To keep collector voltage as well as collector current in proper mode, we will use transistor biasing. So this transistor biasing specially needed for DC to get collector voltage as well as collector current. In transistor biasing, we will use the term operating point. For using operating point, we need stabilization, means stability is needed there to fix proper operating point. So to keep proper operating point, transistor must be in forward bias condition and the transistor must be stable. This is about transistor biasing. After discussing about transistor biasing, I am concentrating on stability factor. Here what is stability factor? Suppose I am replacing one transistor with another transistor. The configuration of one transistor is differ with the transistor of configuration, means parameters here. The parameters design of one transistor is differ from the parameter design of another transistor. So if I replace one transistor with another transistor, the readings is obviously change. Suppose if the temperature is changed, one day the climate is cold, another day it is very hot summer, at that time even the readings will be changed. So here I want the transistor parameters to be fixed if the temperature changes or if I am replacing transistor with another transistor. So that one is called as stability factor. Stability is needed. Suppose whatever is the temperature, but I want the readings in proper way. Another one, if I replace one transistor with another transistor, even the readings does not change. So that particular combination is called as stability factor. So in stability factor, I am concentrating on 2 points. What is the first point? The collector current does not change with changing temperature. Even temperature changes, I don't want to change the collector current. That is the first point. What is the second point we are using? Suppose I am replacing one transistor with another transistor. Even I am replacing one with other, I don't want to get the changes in the collector current. So I want to keep the collector current fixed. Whatever the parameters I am changing, that combination is called as a stability factor. So the definition of stability factor is the ratio of collector current to the reverse saturation current, where beta and voltage from base to emitter is kept constant. This is called as stability factor. So the process of making operating point independent of temperature change or replacement of transistor is called as stability factor. So final conclusion is I want my stability factor fixed. Even changing the environment or changing the transistor, I don't want to change my collector current. This is stability factor. Next we will discuss about thermal runaway. Suppose suddenly the collector current is increasing. If collector current increases, what happens? The equipment will damage. The equipment will damage means first the transistor will spoil. Next what happens? The breadboard, whatever we are using the practicals, it will burn, it will spoil. It will affect the power supply. So even if the changes in the collector current, the total equipment is damaging. To solve that problem, we have to use biasing. So how much it is damaging means whatever the reverse leakage current is produced, that is producing double. for 60 degree centigrade for germanium, for 100 degree centigrade for silicon. So here the overview of thermal run away is collector current is increasing suddenly. If current is increasing suddenly, the transistor will damage, the breadboard will damage, the whole equipment is spoiling. So to solve this damage problem, we are using transistor biasing. So what is the formula of collector current we are using here? The collector current we are using is beta times of base current plus 1 plus beta times of reverse saturation current. Here reverse saturation current is represented with I of CO. Base current is represented with B. Beta is the current gain. So final, what is the definition of thermal runaway? The definition of thermal runaway is self-destruction of transistor is called as thermal runaway. To solve this problem of thermal runaway, I am using transistor biasing. So the next topic we are using is transistor biasing. In this transistor biasing, actually 4 types of biasings is there. What are the 4 types of biasings we are using? One is fixed bias, another one is emitter bias, next one is collector bias, next one is voltage divider bias. So 4 types of biasings is there. So what is the purpose of doing transistor biasing? The purpose of using transistor biasing, if collector current is changing, the transistor is damaging. To solve that problem, we are going for the transistor biasing and 4 types of biasings. The first one is fixed bias, emitter bias, collector bias, voltage divider bias. In that we will discuss the one of the biasing is called fixed bias. What is the figure represents here? This figure is PNP transistor. PNP transistor. In this PNP transistor, here we have collector, this is base, this is emitter. Whatever the voltage is producing from base to emitter, that is called as VBE. B means base, E is emitter. Whatever the emitter is producing from base to emitter, that is called as VBE. Whatever the voltage is producing from collector to emitter, the collector to emitter voltage called as VCE. Next here, across the input terminal, I am connecting one resistor. The resistor what I am connecting is called as a base resistor. This base resistor is represented with RB. This base resistor, from where to where we are connecting? This base resistor is connected from base terminal to the collector terminal. So from base to collector terminal, what are the connections we have? From base to collector terminal, one resistor RB is used, another resistor RC is used. This RB resistor is used across the base, RC resistor is used across the collector. This RB and RC is again connected to the VCC power supply. In the practical, we will take VCC power supply as a plus 5 volts. Next, this collector region to the output is, this is output region. How we will see in the practical? This output region we have to connect it to the CRO. What is here CRO? CRO means cathode ray oscilloscope. So this collector region I connected to one capacitor. The other end of the capacitor I am connecting to the cathode ray oscilloscope. So here across the base terminal I am applying input signal. After applying input signal across the base terminal, where I am getting my output? I am getting my output across the collector terminal capacitor. So here what is the function? So this is the description of the diagram. The description of the diagram is over. Then we will see what is the function of using this fixed bias. The fixed bias usage is, suppose I am taking one fixed value of RB. If fixed value of RB is there, however power supply VCC is fixed, here in the lab we will use VCC power supply as 5 volts. Suppose the resistor, you can use 1 kilo ohm resistor, 1 mega ohm resistor, 220 ohms resistor, which we will use in the practicals. For different resistor values we have in the laboratory. So connect any one of the resistor from base to collector. RB is we are choosing, and supply voltage VCC plus 5 volts is taken. From this we can calculate collector current IC. Now we will see the description of this one. RB is connected between the base and positive terminal of the battery. Using this fixed bias, what is my final conclusion? I want to keep my operating point fixed one. So operating point fixed means what? I want proper collector voltage as well as base voltage. So using this fixed bias method, I am getting base current. Here resistance RB we are choosing. What is the equation from the diagram here? From the diagram vertically you take the equation. VCC equal to IB RB plus VBE. VCC equal to vertical one, left this part IB RB plus VBE. Using this combination I am calculating the value of RB. This is about fixed bias. After fixed bias, what is the advantage of using fixed bias? What is the disadvantage? Advantage of using fixed bias is if one resistor RB is used, you can calculate collector current easily. But what is the disadvantage? Operating point is not stabilizing. Why operating point is not stable? Because suppose temperature is changing. If temperature is changing, operating point is not stable. For that, this is the disadvantage. We are going for the next one. What is the next one I am using? Emitter bias I am using. What is this emitter bias? In the emitter bias, what is the difference with the previous diagram and this one? Here in the previous diagram, there is no RE in the diagram. Just observe the previous diagram. In the previous diagram, across the emitter, no RE. Here is RE is here? No, this emitter is connected directly to the ground in fixed bias, whereas in emitter bias RE is connected to the ground terminal. Using this one, RE acts as a negative feedback from base to the emitter. After act this as base to the emitter, now what happens? Actually collector current is increasing, but by using this negative feedback, here there is a voltage drop across RE. This voltage drop across RE will decrease the base current. If once the base current is decreasing, collector current is also decreasing. So here from where we have to start explanation point, across RE we have negative feedback. Across RE some voltage is dropping. Voltage is dropping, the meaning is voltage is decreasing. If voltage is decreasing here, across the IB also some voltage and current is decreasing. Across this, if it is decreasing, collector current is also decreases. This is the function of emitter bias. After function of emitter bias, again we have equation calculation part in this. We will calculate base current IB equal to VCC minus IE RE by RB. The next one we have is, after this next one we have is BJT, bipolar junction transistor, as a common emitter amplifier. What is amplifier? Which it amplifies the signal here. Again we have characteristics, gain is high, input resistance is large, output resistance is small, and what about bandwidth? Here the main description of the diagram, if you will understand, you can elaborate your answer in the examination. Here first you have to learn the diagram, and the operation of the diagram is important. Here we are using transistor. Across the transistor, whatever the collector is there, above section is collector. Whatever the resistor I am using across the collector is RC. Whatever the resistor I am using across the emitter is RE. Whatever the two resistors I am using R1 and R2 is called voltage divider circuit. This input part, RS and CS, is called as input part. I am applying some signal across input voltage V in. Whatever the signal I am applying across V in, suppose I am applying sine wave, but output is not sine wave. We are getting output as reverse. Just see this beside diagram. Input is sine wave, output is reverse, means input first is positive half cycle I am applying. What I am getting output? I am getting negative half cycle output I am getting, means from input to the output, the phase angle, the image signal is 180 degrees out of phase. So in the examination point of view, just practice the diagram and elaborate the description of the diagram. Input to the output is out of phase. Next, this is the description of the diagram. After description of the diagram, what happens? We are getting gain. Gain equal to V of out by V in, and whatever the input signal I am applying, that is inverted. Inverted means 180 degrees of out of phase we are getting across the output. After this, we will go for the load line. Just the introduction of load line. What is load line here? Actually here this is the diagram of DC load line and AC load line. Fixing proper operating point without input signal is called as DC load line. After applying input signal is AC load line. Just observe the second image. The down part from A to B, A to B CQ is DC load line. In AC load line, for the operating point Q, I am getting the section outside, inside section is lower side. This is about the DC load line. So in transistors, we have transistor components. Again we are studying about fixed bias, emitter bias. Next we are going for the load line. Thank you.